So thank you very much for the invitation, and it's of course a great honor. I'm very happy to be here. So I'll talk about this subject. And first of all, I have to say the complex system does not mean complex analysis. Now, I simply mean systems which are very, very difficult and very complex to be solved, to be addressed. So just to start, let me give you a very, very simple example, which is not, however, the main subject of my talk, because I will mainly talk on partial differential equations, but just to tell you what I'm going to, the type of problem that I'm going to address. I show that you want to solve a linear system, a linear algebraic system, okay? So something that you write A times U equal to F. And of course, F is the data, and A is the matrix. And assume that this system is big, large, very large, right? So dimension, the dimension is NH, we understand what it is H later on, time NH. And NH in the typical application can be of the order of, say, 10 to the power 6 to 9, right? 10 to the power 6, 10 to the power 7, 10 to the power 9, so 1 million, 1 billion, right? Very, very big, right? Now assume that this system is such that the data or the coefficient depends on a coefficient on a parameter mu. And mu is either a parameter or a set of parameters, a vector of parameters. Okay? Of course, the solution will depend on mu as well. And then you solve the problem, and it takes, of course, a lot of time to solve the problem because the system is very big, right? Now, assume that now you want to explore a very broad set of parameters because those have a physical meaning. So maybe you want to explore 100 different parameters, or 1,000 different parameters, or 10,000 different parameters, right? This means that you have to solve the problem 10,000, the same problem. And this is a kind of gigantic endeavor, right? Now, the point is, can I solve this problem by reducing it to a much smaller system, so that I can explore a broad variability of parameters in a very quick time? This is the idea, the basic idea, okay? Now, in fact, I'm a bit more ambitious because I want to solve a partial differential equation with an operator L and the right-hand side F, and still depending on parameters. So this could be a linear partial differential equation or a nonlinear partial differential equation. It could be steady or it could be dynamic, right? It could be time dependent. Okay. Now, how do we solve this equation? Well, you know that when you have a complex equation, almost never you have an exact solution. So you have to solve it numerically. You have to approximate it if you look for a solution, right? So the idea is that you want to replace this equation by a finite dimensional system. You can use many different types of methods. Maybe you know some of them, the finite element method, or the finite difference method, or the finite volume method, and many others. Fourier methods and many, many others. Now, all those methods reduce this equation, partial differential equation, to a linear system, if the problem is linear. If the differential equation is nonlinear, you will get a nonlinear system. But just to simplify things, assume that you have a linear system, a linear partial differential equation, and then you end up with a linear system, exactly like this one. Okay, and NH is the dimension of the linear system that you have. Is an approximate system. Okay, let me make another very simple example. Assume that now L is the Laplacian. So L mu is, say, minus mu Laplacian of U. And here you have then minus mu Laplacian of U equal to F. So the problem that I will consider are more difficult than this one, but this is just to simplify presentation. So this is my equation. This is in a domain omega of R, say 2 or R3, okay, and on top of that I have boundary conditions, for instance equal to 0 on the boundary of omega. So this is the Laplace equation. So this is omega, well, this is a 2D, but you can imagine the 3D now. And for instance, if I use finite elements, I start from this omega and I have to use a partition into triangles. This is a very coarse partition indeed, but in general you have a much finer partition. But this is only with the purpose of illustrating saving and so on and so forth, right? To illustrate what's going on. Then I'm looking for a subspace, for a solution in a subspace, and I look for a solution that I call UH in a space that I call capital VH. This is a finite dimensional subspace, and this is the space of all functions that are continuous in omega, whose restriction to all these little triangles is a polynomial of degree, say 1, just to oversimplify, okay, of t, and we satisfy the boundary condition. All right. So I'm looking for a solution in this space, which is a finite dimensional subspace, and those are the triangles T. Okay. So this problem, this solution, satisfies this equation here. The integral of gradient of UH, mu, integral gradient of UH, gradient of VH, dx is equal to the integral of f times VH. For all VH in the same space. This is the problem that I have to solve actually. Look for UH in VH such that this set of equations is satisfied. Okay? Now, if I choose now a basis of this vector space, so assume that the basis is phi I between 1 and h, this is a basis for VH, for the space VH. Now it's very easy to see that this problem here indeed gives you this system where A is such that its elements are mu, the integral of gradient of phi j, gradient of phi e. And F is a right-hand side whose elements are Fi, the integral of F times Phi. So you can easily show that because of the linearity you have this type of representation. So I have to solve this type of problem. Okay, this is the problem that I have to solve. Now, engineers call this problem a high-fidelity approximation of my original system of equations. So this is the high-fidelity approximation. And this is a big problem. How big is it? Well, if you use this type of representation, the dimension of this space is the number of internal points. Because for every internal point, I can build up a function phi, which is 1 in that point and 0 elsewhere, which is a kind of pyramid, right? So the dimension of the system depends on the number of points. If I have 10 points, like in this case, which is not realistic, I will have 10 by 10. If I have 1 million of points, which is more realistic, I will have 1 million by 1 million. So this is my high-fidelity system. Then again, I change the parameter here, and I would like to retrieve the solution very quickly. But in this case, I have to repeat the whole process, right? So can I reduce this type of complexity? This is my main interest here. Now, to see practical examples where you have this type of, you have to face this type of problem, well, let me show you some practical examples like this one. Now, what you see here is an artery that we have in our body. This is called a carotid artery. We have it in our neck. We have 2 carotid arteries, and so heart is somewhere here, okay? And this brings blood to the brain. So here I'm solving a partial differential equation. At the interior, you use the fluid dynamics, Navier-Stokes equations for blood flow, and then I have the wall that fortunately deforms. The wall of our artery is deformed, and here I'm using an elastodynamic system, which is a hyperbolic partial differential equation, and they are coupled together, right? So here we already see the solution. the numerical solution of a system like this. Of course, here is a nonlinear problem, so much more complicated, but just showing you the solution. Now, to obtain the solution of this problem, it takes for about 1 full day on a big supercomputer. This is the high-fidelity solution, right? Okay. So where are the parameters here? But for instance, the size of this artery, this angle, the viscosity of the fluid, they can change. So this could be, for instance, parameters that we'll like to exploit in my analysis. Okay? So this is another example. Here is the heart. You see, you have two. You know that in our heart we have 4 chambers, 2 atria and 2 ventricles. So here you have the 2 ventricles, and here you see the deformation of the heart during the heartbeat at different instant. So you have initial time, and then after a time, say 1/10 of a second, and then this is after 2/10 of a second, and you see the way the heart contracts and relaxes, right? And the same here. So the only thing that changes from the upper row and the lower row is just one parameter, and the parameter is the orientation of the fibers. So in our myocardium, which is the muscle of our heart, we have fibers. The fibers are there to contract myocardium and also to conduct the electrical field that is generated in our heart at every instant, right? So the only thing that changes from here to there is the orientation of the angle that governs the orientation of the fibers, right? Of course, you change the individual and you may have many different types of fibers. So again, you may be induced to try to start from the problem. This time is a very complicated problem because it's a system of nonlinear, time-dependent, nonlinear diffusion reaction system, coupled with a system of this is for the electrical field, coupled with a system of elastodynamics for the contraction of the myocardium. So very complicated system of partial differential equations, but again, you have a parameter that changes, so you have to take advantage of this fact. All right? This is yet another example. This is the ventricle of a real person, and you see the way it contracts over a heartbeat. This is a single second. You know that the heartbeat takes about 1 second. So this is the way it contracts. Again, we are solving the problem of the electromechanics. And here comes the parameter. Here is the same ventricle, and we are assuming that there is a region which is necrotic because of a stroke, of an infarct, right? And we are changing the size of this necrotic area. In this case, it's very small. This case is much larger, and this case is a kind of intermediate. Okay, and so we are playing now with this region, this necrotic area, assume that this type of shape, and we are just playing with the radius of this semi-sphere, say. This is a parameter, right? So we want to see the way the patient reacts to a situation where you have a necrotic area that changes in size, right? And so on and so forth. Okay, let me now go back and try to go to mathematics. So this was the motivation. And there are plenty of examples of this type in any field of physics, any field of engineering, in biology. You have parameters everywhere, right? Coefficients everywhere, right? Okay. So this is the general setting. We have, as you see, a vector of parameters, mu1, mu2, mu_p. It might be a vector. It belongs to a space that we call P, the set of parameters, right? And then we have a domain, a domain where we want to solve our partial differential equation. Then you have a space where you look for the solution. So for those who are aware of the use of solution of partial differential equations, this is a sober space in general, like H1 or H10. In that case, it would be H10, sober space H10. And then for every mu, our L is an operator going from V to its dual, right? And F is a right-hand side, which accounts for the coefficients, for the data, and goes from V to R. So it's a linear and continuous form on V. So this is a classical setting, And then we want to solve the problem, give a mu belonging to P, find the solution of L times mu equal to F. So this type of problem here, basically. This is the general setting, right? Here's another example. So for some reason, the projector cuts the lower part. I see it on the screen, but you don't see it here, but you just have to imagine, right? You have plenty of imagination because we are mathematicians, so plenty of fantasy. So this is a bypass. A bypass is an operation that you make when you have, say, in this case, you have an artery and you have an occlusion because of some pathological thing, right? And then you create a bypass in order to bring blood to the downstream part. And of course, you have different type of parameters. In this case, these artificial. These are the doctors that create this type of patch. You have the angle between the original artery and the bypass. You have the diameter of the bypass, and then you have, you don't see it here, but you have the amount of flow, blood flow that enters into the artery. And this depends on the blockage, the percentage of the blockage. So these are three parameters, right? In that case, these two are geometrical parameters, and the third one is a physical one. It's the inflow, say. Just to give you an example, right? So we may have physical parameters, geometrical parameters, like the one that you have seen in the previous problem. So this is our basic setting, and then these are the examples that you have seen before, where I described you the role of the parameters, and this is just to tell you that we are not only addressing linear partial differential equation, but general partial differential equation. So if you look at the variational formulation, you have a bilinear form, and then you solve the problem A of u v equal to f of v. So this is the bilinear form for the Laplace equation, okay? But this bilinear form will change depending upon the nature of the original problem. I want to describe the basic principle of the reduction. So this is the high fidelity problem, right? I'm just projecting my equation onto the subspace, pH, and then I'm solving the same type of equation. So this is the high fidelity. High fidelity means very accurate, but also very, very costly to achieve because of the size of the problem, right? So I told you before that for that example, it takes about 1 day for a single heartbeat. If you take, you see the heart that is contracting. Sorry, so this is the typical size, this is the typical amount of time that you need in order to solve the problem, sorry. So we want to speed up this computation because we want to be able to treat it as many patients as we wish, for instance, right? So explore the variability. So assume that your high fidelity problem is well posed. There is a unique solution. So you have to work on functional analysis to show that this is well posed. Assume that you are in this case. And then what are we going to do? Well, we need to introduce a concept, which is the solution manifold. What is the solution manifold? Well, we are solving a finite dimensional problem. The solution manifold is the manifold described by all the possible solutions. So let me make a very simple example. Assume that you have just one parameter, okay? Just parameter, and then one parameter, we have the solution. And so we can describe our manifold in this way. Here is our mu, and for every value of mu, we have UH of mu, the solution, right? We're representing it in this way, and we call this MH. This is the solution manifold. So to compute the whole solution to all manifold, you will have to vary this mu in all its set, its range of variation, and for every mu to compute the corresponding value. This is impossible, of course, right? So the point is, how can you approximate this solution manifold with a much with a linear subspace of very small dimension, so that instead of the solution manifold, we like to approximate a linear subspace, right? And to compute a linear subspace and make sure that the distance between the linear subspace and the solution manifold is small. This is the idea. Okay, of course, we pretend the solution subspace to be of very small dimension. That's the idea, right? So we want to play with the dimension of this linear subspace. It has to be very, very small. In that case, we'll be able to solve our problem very quickly. So the approach that I'm going to use is called RB method, reduced basis method. So reduce because we're going to reduce the dimension, basis because we introduce a new basis of functions, and the method because it is a method of approximation, say. So what is the idea? The basic idea is this one. Here I have the whole set of parameters. For instance, remember the size of the necrotic area, okay? So assume that I'm exploring only few values of those parameters. 5, 10, 20, and for each of them, I compute the solution, corresponding solution, by physically solving my problem. So for every value of mu, I compute the solution. So if this is mu I call this UH of mu I. All right. So let me call it psi I. So the idea is that to find representative values of the coefficient mu I, computing the corresponding solution, and then using the linear subspace generated by these corresponding solutions. Only by those points, right? These, and that. If I select 10 characteristic values of mu I will have 10 characteristic solutions, which are very costly because for each of them I have to solve a problem with millions of variables. But then, when I have a new value, because this would correspond to a new patient, for instance, I have a new value, say one which is here, this is mu. Well, the corresponding solution will be obtained by linear combination of the previous corresponding solutions. This is the idea. Or more precisely, by solving the same problem in the subspace generated by the previous solutions. But this is a very small subspace. Order of 10, order of 100 instead of order of 1 million. So this is the idea. So obviously the most important point here is how well you choose these representative coefficients. If you fail to choose them nicely, your solution will be not that meaningful. This is one aspect of the story. So we look for a solution, when you have a new value of mu, we look for a solution which is a linear combination of the previously computed solutions. Those solutions are called snapshots. So we look for a solution which is a linear combination of the snapshots. We call this solution UN, capital N. Before we have capital N H, now we have capital N. Capital N is the dimension of the subspace, and capital N is much, much smaller than NH. So capital N is much smaller than NH. This is the idea. So we look for a linear combination, and for this linear combination, we pretend UN to satisfy a similar problem as the one that was satisfied by the high fidelity solution, but on a much smaller subspace. Right? So this is the trick. Let me show you an example, a very practical example. I'm solving this equation, which is a diffusion and convection problem. This is the Laplacian and this is the gradient. U is the solution, is a scalar function. This scalar function represents the, say, the temperature in this object here, which is a heat diffuser. And we have, you see here, cuts, and on these boundaries, we apply a thermostat, temperature, certain values of the temperature, and then we want to see the way this, you see this temperature behaving the whole structure here. So what is B? B is a convective field, so it's a solution, for instance, for the fluid flow. This is a possible form of our B, and I want to compute U. Which are the parameters here? I have several. I have, you see, U equal to GP of this gamma I. So I have 3 of them. Then I have, you don't see it here because it's hidden by the whole thing, but it's the Reynolds number, sorry, the Peclet number. The Peclet number is basically the length of B is a vector, divided by U. So it gives you an idea on the way the convection dominates the diffusion. Convection means transport, and diffusion is the molecular diffusion. So we have 4 parameters in this case. I'd like to compute the solution of this problem with these 4 parameters and in a quick way. This is the solution manifold. We have the set of parameters we want to choose. So this is the first one, mu1, and I compute the corresponding solution. What does that mean, mu1? mu1 means a suitable quadruple, right, of values, GP and then the Peclet number. I make a selection of those. I fix those values, and I compute this corresponding solution. This takes for a while because this is a big system of order of 1 million of variables, right? I use finite elements, so my high fidelity solution is finite element. And this is the corresponding solution, the one that have been computed, the first snapshot, and this is one point of this manifold. Then I select the second one in a smart way. We'll tell you later what does that mean in a smart way. And then a third one, and then a fourth one, and then the nth one. So you see, you have solutions that are very different from one another. If you look at the picture, the solutions are very different from one another. And they have to be very different from one another because you want to have a representative sample of all possible behaviors. And then those are computed offline. Offline means once and for all. What does that mean online then? That if I have a new value of mu, I want to compute it as a linear combination with the previous one, and online should be very fast. Offline could be very lengthy. So offline is where you invest, and then you gather your, say, snapshots for future use. And online is when you want to go almost real time, to solve almost real time for a new solution. Okay, so this is the picture. You see the original black and H. And then I use the snapshot solution. I take a linear combination, which means that I have a linear, say, subspace. And for a new value of mu, I'm looking for a solution belonging to this linear space, linear subspace. So I'm basically approximating a linear, a manifold with a linear subspace. This is not obvious that it will work. It depends on the regularity property of the smoothness properties of this manifold. And I will give you an indicator later on, a factor, mathematical factor that tells you when you can expect that the linear subspace can well approximate a manifold, right? Okay, so this is still the same story as before. Now it's more, say, formalized in proper mathematical terms. But let me give you the basic idea at the operational level. How do you proceed to compute your solution on the approximate subspace of the manifold? What does that mean algebraically? How can it be represented algebraically? Well, here you have the full story. The original problem, the original finite element problem, or high fidelity problem was, remember, A times U equal to F. And here I'm denoting H, with H, the fact that this is a solution of the high fidelity problem. By the way, what is H in finite element analysis or in numerical approximation? H is always the grid size. What is the grid size? Well, it's the typical diameter of those elements. H is the typical diameter of those elements. Actually, it's the maximum diameters of all these elements. And the smaller H, the finer is this partition. And the higher will be NH, which is the dimension. The dimension is the number of internal grid points, right? So we have AH, UH equal to FH. This is a vector, this is a matrix, square matrix, and this is UH. How big is it? NH by NH. So just to fix the idea, order of 1 million by 1 million. Okay? What does it mean to use a reduced order model? Well, it means the following thing, basically. you compute a new matrix, which is V, call it V. This is a new matrix. How is it made, this new matrix? Well, it's a matrix whose columns contain the snapshot solutions. You have computed the snapshot solutions, right? Those are finite element solutions. You can characterize a finite element function through the values that it takes at the grid point. So if you have nh grid points, remember this is a piecewise linear function. Okay. So you have the n points, and every point you have a value, and you put this value in the column. And this is the first snapshot. There's in the second snapshot, third snapshot, and so on and so forth. You have a new matrix that we call V. Okay? So this matrix is a rectangular matrix because every column has the size nh, because it's the dimension of the number of points. But how many do we have? N, not nh, the number of snapshots. So this is a nh time n matrix, this V. Right? So what can we do? Well, we can do the following thing. We can represent UH, which is the high fidelity solution, as being V matrix time a vector. What is this vector? This is the vector of the grid values of the reduced solution, the one that we are looking for, right? Which is on the linear subspace. So this is a big matrix, rectangular matrix time a small vector. nh by n time n, those are the dimensions. So I replace UH by this approximation. Instead of having AH-UH, I have AH times VUN. But this is a strange system because I have, you see, NH equations and only n unknowns. N is much smaller than NH. So 10 unknowns and NH equations. I have to close this system, and to do that, I can multiply to the left by V transpose. So now we have a system here whose dimension is n by n, the same dimension as un. And here I have a new right-hand side, which is ft times fh, vt times fh. And this is my new system, this is the reduced system. This is the reduced system. This matrix here, I call it an, it has dimension n by n. This new right-hand side, I call it fn, which has dimension n. And this is a very small system. So this is my new matrix. Very small, 10 by 10, say, or 100 by 100 instead of million by million. This is my reduced system. So if I have a new value of mu, I want to solve this new system instead of the original one. So I have a 10 by 10 system instead of a million by million system. Of course, the whole mathematical intricacy is the way you compute this this V matrix, the snapshot, right? This is the critical point. But assume that you have a kind of magic formula that allows you to compute them very nicely, then the gain is obvious. So this is the reduced basis method. Why reduced basis? Because I have a new basis which is made by this snapshot. Okay, how does it behave practically? We are solving the problem that we had before, the one with the heat exchanger, right? The heat dissipator. And we want to see the way the error behaves when you increase the number of basis functions. So how many snapshots do we use? We go from 1, and the error is basically 1, normalized, to when you have, this is 31, you don't see because you have, you see 31, you don't see the other rows of this table. So this is 31. With 31 snapshots, you have machine accuracy, which is 10 to the power, well, not really, but we decided to stop here at 10 to the power minus 7. This is the error. Error between which kind of elements? This is the error between the high fidelity solution, the one that we get if we solve the big system, and the solution obtained by reduced basis method. So this curve, this is a log-log. So this curve is exponentially decaying, tells you that the error decays exponentially fast. Like the exponent of minus n, n being the number of reduced basis functions. So you cannot be the exponential decay, right? So this is a very fortunate case in which the manifold is very smooth, and this is affected by, you see, the rate of convergence. Okay. For those who are aware with finite element approximation, this is the macroscopic difference. In the finite element analysis, the basis functions do not depend on the problem. They are always the same. They only depend on the discretization of the grid, right? For every point, you take the pyramid, which is given by the function that is equal to 1 in this point, 0 in the other point, and therefore is a pyramid here, and is 0 elsewhere. So the basis functions are problem indifferent. Here, the basis functions are the snapshots, so they depend on the problem. For instance, here you are solving the problem, the fluid around an airfoil. This is the profile of an airfoil. Assume that you are about to design a new airfoil for an aircraft, for instance, and you have parameters. So you see, these are 3 different airfoils. They change because the length changes, this is one parameter, the thickness changes, second parameter, and the so-called angle of attack changes, third parameter, right? So you have 3 parameters. And these are, for these different choices of these parameters, these are the corresponding solutions. You see, very, very different one another. Okay? So these are snapshots of solution. Here, if you use the finite element analysis, the high fidelity problem, the solutions, the basis functions are, again, problem indifferent. Here, they depend on the problem. And this is why you can take advantage of the fact that you can use very few number of basis functions to get a very high accuracy. Because those basis functions bring a lot of information about the physics of the problem. Okay. Now, a few comments. Say two basic remarks. What makes this method accurate and what makes it efficient? Accuracy and efficiency. If you work in numerical analysis, this is kind of basic dictionary, right? Accuracy means that the error that you generate with respect to the exact solution goes to 0 when the dimension of the problem goes to infinity, and goes to 0 very quickly, hopefully. So the rate of convergence is very high. Efficiency means that the price to pay to get the solution is hopefully very low. So those 2 things in general are fighting one against the other. But this is the whole art of the matter, actually. So what makes the method accurate, as in the case that we have seen before? Well, you can introduce a concept, which is a mathematical concept. It's called the Kolmogorov n-width of the manifold. What is the Kolmogorov n-width of the manifold? So let's make a very abstract argument. You do have a manifold, right? Any type of manifold, and you want to see how well you can approximate this manifold by a linear subspace of a given dimension. So I give you a manifold, and I give you the number 25, and I ask you how well can you approximate the whole manifold by a subspace of dimension 25, okay? Or 32, or 158, right? This is little n. So this is this value, little dn, d is a distance, of nh from vh, is the inf of a sup of an inf. Okay? So the inf is made on all possible subspaces of dimension n, 25, right? This is the distance is a sup, and this is the inf. This is the inf between uh of mu, which is the single element of a generic element of my manifold. Don't forget that the manifold is a solution manifold, minus Vn. So this is the inf on Vn in capital Vn, the sup for all possible parameters. The manifold describes all the solution corresponding to all the possible parameters, and this is the infimum that you can get, which is the best possible subspace. So this is called Kolmogorov n-width of nh. this is a concept from approximation theory in infinite dimensional spaces, basically. So if the Kolmogorov width is small, right, you can expect that the reduced basis method reproduces an error which has the same size as the Kolmogorov width. So the accuracy of your method is governed by, or is driven by, this coefficient here, this parameter here, right, which is a theoretical parameter, basically. Of course, you have to prove it, right, and you can prove it in many different cases, not in the most general case, because it's a very difficult problem. This is the this is about the accuracy, and this is what I was telling you before in wording, and this is what you actually get. Now, what makes it efficient? Well, it seems that this is a silly question, because I told you many times that you go from a problem of million by million to a problem by 10 by 10 or 31 by 31, say. It's obviously efficient, right? Because solving a problem of 31 by 31 is, you can do it immediately, right, real time. But the real problem is that these matrices, 31 by 31, depend a priori on the large dimension. You remember the matrix V before, right? The matrix V contains NH information n times. So it is true that once you have formed the matrix AN, the solution is quick. But to form the solution AN, you have to pass from the infinite, from the big system, right? Now, to be efficient, you have to remove this kind of weakness or constraint. You have to be able to generate the finite element, the reduced basis matrices independently of NH. This is the big challenge. It might seem impossible. In fact, it is possible in some cases, and those cases are what they call those of the affine parametric dependence. So we are assuming that our original problem has an operator, or more precisely, an associated bilinear form that can be the sum, the finite sum of bilinear forms that do not depend on the coefficient mu times factors that depend on mu. This is called affine dependence property. Assume that this is the case. You have this, your bilinear form that depends on mu can be represented as a finite linear combination of bilinear forms that are independent of mu. If this is the case, you win. You can show the algorithm. This is pure linear algebra, nothing really, smart here, that allows you to form the matrices in a way that are independent of, with a cost that is independent of big N. So in algebraic terms, it means that your high fidelity matrix, which depends on mu, is the sum of high fidelity matrices that do not depend on mu, time coefficient that depend on mu. If this is the situation, then great, okay? And here are examples where you have these type of situations, right? So this is, for instance, flow in a channel. In this case, you have like physical parameter with the Reynolds number. The Reynolds number is an indicator of the instability, potential instability of the flow. You have, if you work in fluid dynamics, Reynolds number is your, driving factor, right? So it's the velocity of mu times the length of the channel divided by the viscosity of the water, of the fluid, say. So here we are changing the Reynolds number, and we have different type of solutions. Okay. The higher the Reynolds number, the more vorticity you have, and you have secondary flows or tertiary flows, and so on and so forth. So this is a case which is where you have this affine dependency condition satisfied. So this is a nice case. The problem is nonlinear. The problem itself is nonlinear. The PD is nonlinear, Navier-Stokes equations. But the dependence on the parameter of the solution is affine. This is another case. Same type of thing. Now you're playing with the geometric parameter. Now this is your step, right? The channel. And you're playing with those parameters, see, the Reynolds number and the channel height, the scaling basically, right? And again, this is a finally dependent. So again, you can take advantage of this property. This is not affine. This is a linear equation and still is not affine. Why? Because your source term represents, in this case, you see, the position of the so these are advection diffusion reaction problem. Assume that you are simulating the emission of a pollutant from a chimney. You want to express the right-hand side as being the source. And therefore, you have the coordinates of the points where you have your chimney, right, in your computational domain. This is not affine. If you change your chimney, the solution will not, the structure of the problem will not depend in a linear way. So this is not affine. Okay? So you can build up many, many different problems. Some of them are affine and others are not affine. Now, of course, it's a long story, but let me just anticipate the conclusion. The conclusion is that if you have the affine dependence, there's no problem at all. The problem is accurate and efficient. If it is not affine, you have to modify the method. You have to basically interpolate the non-affinity dependence. So you have an extra process, which is based on interpolation, that, however, allows you to get, at the end, a problem which is only dependent on little n. So it's very small dimension and it's computationally efficient. You call those type of processes the hyper-reduction, because you have two types of reduction. The first one is the finite dimensional subspace, or your manifold, and the second one is the non-affine terms. You need an extra reduction because you need to use interpolation set. But I mean, the conclusion is nice in the sense that you can play with a method which is accurate and efficient. Of course, you can apply it to a time-dependent problem, so dynamical systems, and for a dynamical system, t is a parameter. Is a further parameter in case you have other parameters. If you are just have a dynamical system with no other parameters, t is the parameter. Okay. You can apply it, as I was saying before, to the case of nonlinear PDEs, and you have this hyper-reduction story, and here is the presentation of the basic elements. So let me conclude by showing you some further kind of elementary application. The original ones were more demanding. This is an aneurysm for an aorta. This is the aorta. This is a bifurcation, it's a natural bifurcation, and this is an aneurysm. An aneurysm is a pathological inflation of the aorta. It's risky because if it breaks, it's a big issue, right? So we want to solve, for instance, the fluid dynamics and the mechanics because you want to compute the stresses to see if they are below or above a certain threshold. So you have these equations. Those are the equations for the nonlinear mechanics, and then you have parameters that describe the nature of the aneurysm. For instance, in that specific case, those parameters describe in different regions of the aneurysm different values of the Young moduli or the Poisson moduli. Of course, the aneurysm is made by different type of material because you have plugs, you have a calcified material, or you have elastic material. So those parameters describe how healthy or how unhealthy are the different pieces. Right? So this is non-affine dependence. You need to develop this hyper-reduction that I was telling you before, and this is the corresponding solution. You see, we are computing here the high-fidelity solution with finite elements and the reduced solution. The high-fidelity solution requires, say, 500,000 degrees of freedom, unknown, say, so capital NH is, roughly speaking, 0.57 million. Right? The CPU time that is required on a processor with 10 nodes is 300 seconds. Now, with this is a small case, this is a big case, larger case. This is 3.8 millions, and in this case, the CPU time is 1300 seconds on 20 nodes. Okay, so this is the solution. You see that you need this type of dimension because the solution here is very, very different than the solution there. So those are the von Mises stresses. And these are the values of the von Mises stresses. Red is the highest and blue is the lowest. Right? So you really need to go there because otherwise the solution here would be, you see, is very different than there. So you are very far from convergence. So this is the size of the system you have to solve in this specific case. Now, when you solve it with the reduced basis method, we characterize different regions with different values of the coefficients of the moduli. And here we are comparing, in all cases, the finite element solution, which is the high fidelity solution, with the reduced order model solution, right? And you see the pictures in the I norm, they are basically the same, right? This one and that one, this one and that one, and the same here, right? Now, this is a shocking number because it takes you 54 seconds on one note on your PC. Before it was 1300 seconds on 20 nodes on a parallel computer with 20 nodes. So this is the gain that you can have in this specific case. And this is a non-trivial problem, right? And okay, here there are other examples again that shows what's going on. This is a bypass in the femoral artery. So this is the original, let's say, femoral artery, and you see is blocked here. This is restricted. This is because of a plaque. That's why you create, say, a bypass, and this is the solution that you get. You are solving here the Navier-Stokes equation coupled with the nonlinear elastomechanics problem, very, very big problem to solve, and is solved in a time which is real time. So we are solving a pulsatile flow for 1 second, a pulsation, it takes 0.1 second of computational time with the reduced basis method. So you can really get an incredible advantage in those cases that work nicely. So this is yet another example. This is a cerebral aneurysm, and you have similar type of results. Okay, I think I'm going to stop here, but I'd like to tell you where we are actually using this type of approach. We use it for the simulation, so the solution of partial differential equation, and this was the subject of my talk. But indeed, we use it also for controlled optimization. When you have to control a system, optimize the system, well, this is much more computation intensive than just solving a single shot, a single problem. Or we use it to quantify uncertainty. Assume that now the coefficients here are uncertain. How can you control the propagation of uncertainty on the solution? This is one example, right? So you have to quantify the uncertainty in the system, and this is extremely costly from the computational viewpoint, and this is where you actually take advantage of reduced basis method, because for every time you have to solve the forward problem, you take advantage of the reduction. So this was just a very, very elementary introduction to a field which is very, very big, and it's, I mean, theoretically challenged from the mathematical viewpoint because there are so many concepts from so the theory of PDEs, the theory of numerical approximation, and of course the linear algebra theory. And on the practical viewpoint, you have basically parameters. Every time you touch a problem, a physical problem, a real life problem, you have coefficients, we have parameters, we have elements that provide the richness of your problem. And this is a possible answer to all those type of challenges. So thank you very much.
So thank you very much. So are there any questions?
So regarding your reduced systems that you get, usually condition numbers.
Okay, very good question. Now, the original system is a condition number that depends on the order of the operator and little h. So typically, if you have a Laplace equation or an elliptic equation, the condition number is h to the power minus 2. So for those who are unaware of this type of terminology, condition number is, roughly speaking, the maximum eigenvalue divided by the minimum eigenvalue of the matrix. So the higher the condition number, the more difficult it is to solve the system. So this is a typical condition number of the matrix, original matrix. Now for the other matrix here, the condition number behaves in a much worse way with respect to capital N, of course, right? So the dependence on capital N is much worse than the dependence on 1 over h. But capital N is very small. So it's order of 10, order of 100, so you do not really care. And you use a direct method to solve the system. Here you have to use iterative methods with preconditioner. Here you use direct method and takes for nothing. But it's true that the matrix here is full because snapshots, of course, are global functions. So here the matrix is sparse. Here the matrix is full, but it's so tiny that you do not have any problem in solving it.
You obtained this approximation subspace, and you said that it depends on the regularity of the solution manifold. Wouldn't it depend strongly on the topology of the manifold? Because I find it sort of surprising that you don't.
Sorry, if I need what?
Does the approximation subspace,
yes.
the existence or the
yeah.
quantity of the approximation subspace, doesn't it depend on the topology of the solution manifold?
I don't know. I mean,
which you don't know.
No, hopefully not. I mean, this is a constructive method. So you give me any solution manifold, right? And I find the representative values of ui, and I compute these values here, right? So in any case, I know how to compute a subspace, even though I totally ignore the solution manifold.
Yeah.
So from the constructive viewpoint, the method is blind to respect to the knowledge of the. However, from the theoretical viewpoint, the accuracy depends on the smoothness of the solution manifold that you might not know. In some cases, you can characterize it because it depends on the differential operator. So in some cases, you know that. In other cases, you do not know. And indeed, you see that a posteriori, you have fantastic accuracy in some cases and much worse accuracy in other cases. And this is basically an indirect appreciation of the quality of the solution method, of the solution manifold. However, the regularity here is not the Sobolev regularity of the solution. Is the regularity of the solution with respect to the view. It's a totally different type of concept. Yeah. So it's a totally different type of concept. Yes.
So are there any more questions? If not, let's thank again Alfio.
Thank you.